Hello, this is Professor Roman. Let's continue the field theory lectures. We have studied several classes of field extensions so far: the finite extensions, the finitely generated extensions, algebraic extensions, transcendental extensions, and separable extensions. Let's consider now another very important class of field extensions, especially for Galois theory, the normal extensions. I want to begin by recalling some facts about splitting field extensions. So let f bar be field extension, a splitting field in f bar for a non-constant polynomial p of x over f is a minimal extension field S of f in f bar over which p of x splits. And by that, of course, I mean factors into a product of linear factors with a constant also. We're also going to say that the extension fs is a splitting field extension. The family of the multiset of elements R1 through Rn is a complete multiset of roots for this polynomial. There can be no other roots for this particular polynomial, not in f bar. And I will let you think on why that is. Okay? So this is a complete root multiset, R1 through Rn. And the underlying set, because some of these may be equal, we'll call a complete root set for the polynomial in f bar. If you change the algebraic closure, you will get potentially different roots. More generally, let P, script P, be a family of polynomials over f, non-constant polynomials. A splitting field in f bar for P is a minimal extension field S of f in f bar over which P splits. So to say the family splits, as I mentioned before, is to say that every polynomial in the family splits. And we'll call the extension fs a splitting field extension in f bar for the family P. And we'll call the collection the multiset of all the roots of all the polynomials in the family, all the roots that lie in f bar, of course, as a complete root multiset for the family. The underlying set is a complete root set. The complete root set is the union of the complete root set of each polynomial. We had an earlier theorem, let P be a family of non-constant polynomials over a field F, then in any algebraic closure f bar of f, there is a unique splitting field for P. And I left that as an exercise. Here is one possible proof. Since f bar is algebraically closed, the family P splits over f bar, and so contains a unique complete root set R for the family. And I'll let you ponder that. There is an issue here. You might think about a single polynomial first. How do you know that there couldn't be two factorizations of p of x into constant times linear factors? You have to think back on the issues of irreducibility and primeness in a principal ideal domain. So in any case, there is a unique complete root set R for the family in F bar. Then the family splits over F with R adjoined. It has all the roots. But it doesn't split over any proper subfield, say T of F with R adjoined, because there must be a root, little r and r, that's not in T. Otherwise T wouldn't be a proper subfield. And so any polynomial in P that has r as a root, and there must be at least one, is not going to split over T. So the family will not split over T. Therefore, by definition, F with R adjoined is a splitting field. It's a minimal field under which, or over which, I should say, the family splits. As far as uniqueness, if S is a splitting field for the family in F bar, then F is contained in S, and the roots, the unique root set R must be in the splitting field. And so F with R adjoined is in the splitting field. But then the minimality of S as a splitting field implies that equality holds here. And so in fact, F with R adjoined is the unique splitting field for the family of polynomials in F bar. Well, splitting field extensions are very important. And so we should take a closer look at them. Suppose first that Fs is a splitting field extension in S bar, which is also an algebraic closure of F, for a family script P of non-constant polynomials. By factoring any reducible polynomials in the family, reducible over F, we're going to change the family potentially if we have to factor something, but we're not going to change the splitting field because we're not changing the root set. And so we can go ahead and assume initially that the polynomials in the family are irreducible. We could also assume that no two polynomials in P are associates because they have the same roots, and so we can eliminate any associate polynomials. And so the root sets of the polynomials in our adjusted family, which I'll just call P, are pairwise disjoint. Furthermore, we have seen that the splitting field S is F with the root set adjoined. And so R is the disjoint union of the root sets of the individual polynomials in P. Okay, now, since any embedding sigma of the splitting field S into S bar over F sends any root alpha in R of, say, the polynomial P of X to a root of P of X. It sends roots to roots because it fixes the base field pointwise. It's over F. So it follows that sigma is in fact a permutation of the root set for each polynomial. It's injective. It sends the root set into itself. The root set's finite because we're talking about a single polynomial now, and therefore the sigma is actually surjective on that root set. It's a permutation of the root set. Well, it's a permutation of each root set, therefore it's a permutation of the disjoint union that makes up the root set for the entire family. So sigma of R is equal to R. And therefore sigma of S, which is sigma of F with R adjoined, is F with sigma R adjoined, because again sigma fixes F pointwise, and so that's F with R adjoined, which is S. So sigma maps S onto S. So we have shown that the embeddings of our splitting field into an algebraic closure over F are actually the automorphisms of S over F. It looks like that. So the splitting field extensions have this property. Conversely, suppose this property holds for an algebraic extension, Fs. So I'm not assuming this is a splitting field anymore, just an algebraic extension. And let alpha be in S. It'll have a minimal polynomial over F. Since for any root beta in S bar of this minimal polynomial, there is an embedding of S into S bar over F that sends alpha to beta. We discussed this much earlier in the chapter. So this equation tells us that sigma, this embedding, is actually an automorphism, which means that the image beta of alpha is in S. In other words, every root of this minimal polynomial is in S. The minimal polynomial splits over S. Alpha was an arbitrary element of S, so every minimal polynomial splits over S. Accordingly, S contains a splitting field for the family of minimal polynomials of the elements of S. But, similar argument to before, no proper subfield T of S could be a splitting field for this family, because if there's an element alpha in S that's not in T, then that minimal polynomial does not split over T because it's missing the root alpha. So Fs is in fact a splitting field extension for this family. So this condition characterizes splitting fields. And it's worth noting that this family of minimal polynomials, all of the elements of the field S, is the same as this family is the same as the family of all monic, irreducible polynomials over F that have a root in S. Those are precisely the minimal polynomials. So we have three ways to characterize these extensions we're talking about. The following are equivalent for an algebraic extension Fs. It's a splitting field extension for a family of polynomials. These would be non-constant, I should probably say that. They have to be because that's the only time splitting fields are defined, but it's still good style to state that. As I've said before, all these little minor problems will be cleared up before I post the book on my website. Fs has the property that every embedding of S into S bar over F is actually an automorphism of S over F. So that's this condition. And finally, every minimal polynomial over F splits over S. Another way to say that is every irreducible polynomial over F that has a root in S splits over S. Another way to say that is that S is closed under conjugates. Remember, that two elements are conjugate if they have the same minimal polynomial. So an algebraic extension that has these three properties, if it has one, it has all three, is called a normal extension. And we say that S is normal over F. Here is a corollary that will be useful at times. An algebraic extension can be written this way, F with S adjoined, where S belongs to F bar. This is normal if and only if it is the splitting field extension for this family of minimal polynomials. This is not all of the minimal polynomials. Let's not be confused here. Here S is a field. Here S is simply a subset of F bar. It's the generating set for this field. So this extension, which is a general extension, algebraic extension, is normal if and only if it's a splitting field for just this smaller family of minimal polynomials of the generators of S. As to proof, we have seen that if this is a splitting field extension for this family, then it's normal. That's one of the defining conditions. Conversely, suppose this extension is normal. We want to show it's a splitting field extension. Well, we can let Fk be the unique splitting field extension for this family in F bar. In F bar, there's only one such extension. The previous theorem tells us that M splits over F with S adjoined because this is normal. And so K is a subfield of F with S adjoined because K is a minimal field over which, in fact, it's unique in over which the family splits, and it's unique in F bar. Okay. But on the other hand, F is a subfield of K, and S is contained in K, and so Fs is a subfield of K, and we have the two subfield relations, so they're equal, and Fs is the unique splitting field for the family M over K over F. When we study Galois theory, we will later on we will see that there is a connection between normal field extensions and normal subgroups of the Galois group. And that accounts for the use of the term normal for these field extensions. We could just call them splitting field extensions and not use the term normal. But that term normal is standard terminology, and the reason is because of this connection. It'll be a little while before we get to that. Another corollary of the theorem is essentially the same theorem, but for finite extensions. So the following are equivalent. Fe is a finite normal extension. E is the splitting field of a finite family P of irreducible polynomials over F, and I don't really need that. If it's a splitting field of a finite family, it's also a splitting field of a finite family of irreducible polynomials by factoring, so can take that out. E is the splitting field for a single polynomial over F. So finite normal extensions are splitting fields for a single polynomial. As to the proof, if Fe is a finite normal extension, then since it's finite, it is of this form, E is of this form for a finite set S. And so the corollary we just discussed tells us that Fe is a splitting field extension for this finite family. These are the minimal polynomials for the elements of the generating set. So that means, and that's a finite family, because S is finite, and so that means 2 holds. Okay? And you can see why I put irreducible here, because they're minimal polynomials. If 2 holds, then E is the splitting field also for the product of the polynomials in here. Since this is a finite family, we can take the product of these polynomials, and that, of course, is a single polynomial. And finally, if Fe is a splitting field extension for a single polynomial P of x over F, then E is normal. It's a splitting field extension. And it's also finite, because it's finitely algebraically generated by the roots of P of x. So that's 1. I should note also that this extension, FF bar, is normal. And I'm sure you can fill in the reason. Here is a theorem, very important actually, whose proof I'm going to leave for you. It should only be 1 line or 2 lines. Any extension Fe of degree 2 is normal. Let's now examine the distinguishability properties for the class of normal extensions. The class of normal extensions fails miserably to satisfy the tower property. Let's look at this example. Rationals Q, Q with the square root of 2 adjoined, Q with the 4th root of 2 adjoined. Each step has degree 2 and is therefore, by the theorem I just discussed, normal. But the full extension is not normal because x to the 4th minus 2 is irreducible over the base field here. But this polynomial contains exactly this field contains exactly 2 of the 4 roots of this polynomial. So this polynomial has a root in here, but it doesn't split over this field. Okay. Also, the full extension in this tower is normal, but the lower step is not normal. We just discussed that. So here is the full story on distinguishability for normal extensions. If we have a tower, if Fe is normal, the upper step is normal. And that's it. No other tower properties hold. Okay. Closure under lifting does hold, and closure under arbitrary composites and intersections holds. As to proof, for part 1, the only thing we need to check is that the upper step is normal. Well, a splitting field for a family of polynomials over F, so if Fe is normal, it's a splitting field for a family of polynomials over F. That's also a splitting field for the same family thought of as polynomials over K. Okay. And that takes care of the upper step. It's normal. It's a splitting field extension. For part 2, if Fe, and E can be written as F with R adjoined, is a splitting field extension for a family of polynomials with roots at R, and this is in F bar, then the composite EK is EFR, which is the same as K with R adjoined. And I suggest you give that a little bit of thought. And so KEK is the same as KKR with adjoined, is a splitting field extension for the same family F, again, thought of as polynomials over K. For part 3, first to the join, we have a family here of fields, all contained in some larger field K, so we can take the join. If we need to show that if all these individual field extensions are normal, so is F the join of the family and F the intersection of the family. For each index I, this field can be written as F with the root set adjoined. It's the complete root set in K bar for some family of polynomials over F. So the join of EI is the join of F with RI adjoined, and that is F with the union of RI adjoined. And you should probably give that a moment's thought. And since the union of Ri is the complete root set in K bar for the union of these individual families of polynomials, it follows that this is normal. For the intersection, first note that every irreducible polynomial P of x has a complete root set Rp in K bar. So suppose that an irreducible polynomial P of x has a root alpha in the intersection. Then the root set R sub P for this polynomial in K bar lies in every field E sub I. It has a root in the intersection, therefore it has a root in every one of the E sub i's, therefore it splits over each E sub I, so it has this root set is in every one of these family members. So the root set of P of x is in the intersection. In other words, P of x splits over the intersection. So if P of x has a root in this intersection, it splits over the intersection. That means this is normal. We have used two different characterizations of normality here. Well, we have seen that the tower property fails pretty badly for normal extensions. We do know that if the full extension in a two tower is normal, so is the upper step, but the lower step need not be normal. However, determining when the lower step is normal is of critical importance to Galois theory. So let's take a closer look, see what we can learn. So we have a two tower of fields and the full extension is normal. First, we can make the following observation. If we take an automorphism of E over F and we restrict it to K, we get an embedding of K into E over F. And that, of course, is also an embedding of K into E bar over F. But the normality of Fe tells us that any sigma in this set here, embedding of K into E bar over F, can be extended to an embedding of E into E bar over F, which by normality of Fe is the set of automorphisms of E over F. So sigma bar, then of course its restriction to K is sigma. That's what we got sigma bar from. And so sigma is the restriction to K of sigma bar, which is a member of this set. Sigma bar belongs to the automorphisms of E over F. We restrict it, we get sigma. So we have, in fact, this inclusion, and when you compare this to this one, you see we must have equality throughout. So the normality of the full extension, never mind the lower step, tells us that the restriction to K of the automorphisms of E over F are the embeddings of K into E, and that's the same as the embeddings of K into E bar. Well, this gives us two characterizations of the normality of the lower map. This is the first one. If you replace this by this, you get the definition of normality for Fk. The embeddings of K into E bar over F are the automorphisms of K. But since these two are equal because the full extension is normal, we have Fk normal if and only if these two are equal. And because this is the same as this, we can replace this again by this. Or you can replace this one by this, or this one, it doesn't matter. Okay. So we have two ways to characterize the normality of the lower step. And actually there's another way. Let's look at this again. This implies that any automorphism E over F, when restricted to K, is an automorphism of K, so it maps K onto K. What about a converse? Well, if any automorphism E over F maps K to K, then when we restrict such an automorphism to K, we still have an embedding when you do the restriction, but it also maps K onto it. It's an embedding of K into E, but it maps K onto itself, so it's an automorphism of K. Now that's not quite the converse here because we have inclusion. But the automorphisms of K over F are embeddings of K into E bar. So that could go here. So that's contained in this one, and that's the reverse inclusion here. And so we have automorphisms. The restriction of the automorphisms of E over F to K are the automorphisms of K if and only if each one of these automorphisms maps K onto itself. So we have now three characterizations of the normality of the lower step. Here's our two-tower, full extension, normal. These three things are the same. That's what we learned. And so the normality of the lower step can be characterized in three different ways. This is very close to the definition. We have E here instead of E bar. This is the second way, and this is the third way. And we're going to find use for these characterizations. Let us now suppose that we have an algebraic extension, but it's not necessarily normal. It might be by accident, but it may not be. The extension Fe bar is normal. And so the family of all fields, K, that lie between E and E bar that are normal over F is non-empty, because E bar itself is in this family. We can therefore take the intersection, which I'll call N, of this family, and this is the smallest element of the family, because the family is closed under intersection. Being an intermediate field here is closed under intersection, and being normal over F is closed under intersection. So N is the smallest field intermediate between E and E bar and normal over F. This field, N, is called the normal closure of E over F in E bar. And I will use this notation. I imagine there's a variety of notations, but this one seemed reasonable. I'm generally going to drop the subscript E bar here. It's not a serious problem because of the following theorem, and the proof is left to you. If Fe is an extension, E bar and E prime are algebraic closures of E, the corresponding normal closures of E over F, one in E bar, one in E prime, they are isomorphic. So the normal closure of E over F is unique up to isomorphism. So we don't really need to make too much fuss over which algebraic closure contains the particular normal closure. So NC of EF, the normal closure of E over F, is the intersection of all intermediate fields between E and E bar that are normal over F. That's not necessarily the most useful description, so there are some other descriptions of normal closure. Here's one that will come up when we study solvability by radicals in a later chapter. Let Fe E bar be algebraic. It is algebraic because Fe bar is algebraic. The normal closure of E over F is the join of the images of E under all embeddings of E into E bar over F. So it looks like this. You may be thinking now, how can this be very useful if this one isn't? This looks even worse. Well, you'll have to stay tuned for that. So, as to proof, let's denote this join here by J. So J, we have F, J, E bar, because we're taking the join sigma E. Notice what's going on here. Sigma maps E into E bar, so sigma E belongs to E bar. And this join sigma, one possibility for sigma is the injection, the inclusion map. And so one possibility here is E itself. So the join lies between E and E bar, actually. But this is an algebraic extension, or an algebraic tower. What we have to show that J is, we must first show J is normal over F. So that means that one characterization of normality, that the embeddings of J into J bar over F are the automorphisms of J over F. And J bar we can take to be E bar. We can take any algebraic closure of J we want here. So we'll take it to be E bar. Now, note first that if we have one of these embeddings here, then sigma E sits here, and of course it's then contained in the join of all the sigma E's. And so sigma actually maps E into J. Therefore, if tau is an embedding of j into j bar, that's one of these guys, then tau sigma maps E into E bar. E bar and j bar are the same. Okay, sigma goes from E to j, tau picks up from j to j bar or E bar, because I'm taking j bar to be E bar. So just to be clear, j bar can be any algebraic closure. I'm going to take it to be an algebraic closure of E. Okay. So tau of j is tau of this join. The tau goes inside the join, and so we get this. Now each of these is an embedding of E into E bar applied to E, so it's of this type. So we have a join here of fields that are of this type. So we can say immediately that this is contained in this join. They may be equal, but we're not sure. So tau maps j into j, and that's what this says. Any embedding of j into j bar, tau, actually is an embedding of j into itself. Of course, any of these is one of these. We had an earlier theorem that because this is algebraic, the embeddings of an algebraic extension into itself over F are the automorphisms of J. So this is equal to this, and that's what we wanted to show. And so Fj is normal. This is rugged stuff. It takes a bit of study. So don't be discouraged if this all seems very confusing. It's a matter of going over it enough times until it's not confusing. I guess that's true about all mathematics. Well, we must still show that J is the smallest normal extension of F lying within E bar. We know that the normal closure of EF is this intersection. But J lies in here, we've discussed that, and now we know Fj is normal, so J is one of these K's, and therefore the intersection here is contained in J. On the other hand, every embedding of E into E bar over F can be extended to an embedding of N into E bar over F. But that, because N is normal, these are the auto over F. These are the automorphisms of N. And so sigma takes E into N. Sigma V is a subfield of N. And so the join of all these sigma E's, J, is a subfield of N. And we already had N subfield of J, so they are equal, which is what we wanted. A couple of other results related to normal closure. Suppose we have an extension here, Fe, and we write E as F with S adjoined. S is a subset of F bar, so this is an arbitrary algebraic extension. You know, if worse comes to worse, S could be E itself. F with E adjoined is E. Okay. Hopefully we can find a smaller subset of F bar that generates E, but it doesn't really matter. The normal closure of E over F is the splitting field in F bar of this family. We've seen this family before when we discussed when is FS normal. It's normal if and only if it's the splitting field for this family. We're talking about something a little different here. We're not asking when is this normal. We are asking what is the normal closure of this extension, and it is the splitting field of this family. And if we take S to be all of E, it's this family. So the splitting field, split M we'll call it, of F bar, in F bar of this family is of course normal over F. It contains S, and so F is contained in Fs. These should be less than or equal to through here. And the splitting field of M is normal over F. So the normal closure of Fs over F is contained in the splitting field of M. But if we have an intermediate field between Fs and F bar that's normal over F, then for any element of S, this polynomial, the minimal polynomial, has a root in K, and so splits in K, because K is normal over F. And so the splitting field for M is contained in K, and so the splitting field for M is contained in the normal closure, and so again we have equality. Finally, for normal closures, if this extension, again I have to have less than or equal to's here, it's just a notational issue. I didn't mean for these to be proper. If Fe is finite extension, then so is F normal closure of E over F. If Fe is finite, then it has a finite basis, S, and so E is Fs, where S is a finite set. The normal closure is then the splitting field for a finite family of minimal polynomials, and is therefore finite. The last item of business for this chapter is actually another class of field extensions, but we already know pretty much everything we need to know about it. An extension Fe that is both normal and separable is called a Galois extension, or simply Galwa. As to the distinguishability properties, well, separable extensions are strongly distinguished. They have all the properties. And they're closed under intersection, too. I don't know if I mentioned that, but that's, the property of separability is a property of elements, so I'm sure you can sort that out. But normal extensions aren't quite so nice when it comes to distinguishability, but this means that the Galois extensions properties coincide with the properties of normal extensions. So the full extension Galois implies the upper step is Galois, and that's it. Closure under lifting, closure under arbitrary composites, and intersections. And one last item. If Fe is a finite Galois extension, then the set of these are cardinalities here. The cardinality of the set of automorphisms of E over F is the same as this cardinality, because these two sets are the same because of the normality. And this cardinality is the separable degree because of the separability of Galois extensions. That's the definition of separable degree. This is the reason that the equality here is because Galois extensions are separable. Okay?